So now we are about to start with this new chapter called alternating currents. And one of the most important places where we look at alternating currents is in the working of an AC generator. So this is the diagram for a simple AC generator. It consists of a rectangular coil which is rotating in a uniform magnetic field. Now we can ignore these details for now, but the bottom line here is this, that as the coil is moving through this magnetic field, at all the different positions it will have when it's rotating, it will be cutting the magnetic field lines at different rates throughout. So now that will lead to a different, basically to a varying rate of change of magnetic flux linkage, and hence that will also lead to a varying EMF in this coil. So that information can be seen in this diagram. So with the coil in a horizontal position, the coil would be like this. It would be horizontal and the field lines are going from left to right. So when it just starts to move at this position, it would be cutting through the field lines at the greatest rate, and that would lead to a maximum EMF. Now compare this with the position where the coil is vertical, and right at this instant that is shown in this picture here, it's going to be moving parallel to the field line, so it's not cutting field lines at the moment. That will lead to a zero EMF. Again, at this position, it will now be moving in an opposite direction. So now it's going to cut field lines like this. So it's again in the horizontal position, but previously it was moving up. So now this is moving down. So again, by Lenz's law, this EMF will be the same in magnitude, but opposite in polarity, and again the same thing here as well. Since this is now again vertical and moving parallel to the magnetic field lines, no EMF is induced here. Now this thing in itself is not very important, how an AC generator works. I just wanted to tell you guys that in this one, a varying rate of magnetic flux linkage leads to what the name of this chapter is, which is alternating current. In this case, it's alternating voltage, and you know it's the alternating voltage which leads to the alternating current. So it's the same thing. So what actually is alternating voltage or alternating current for that matter? How do we define it? So to talk about the alternating voltage, it would first help us if we talked about the direct voltage or the direct current, which is what we've been using up till now. In all of AS, we never had a look at alternating voltage or alternating current. All we were talking about was direct current. In one word, this means that direct current means that the current is unidirectional. So the current always flows in the same direction. So current is always in the same direction, and obviously that would also mean that the voltage is in the same direction. So on a graph, again, if we talk about current or voltage here, it's the same thing. So V or I means the same thing. What we get, for example, what we get through our batteries is a value like this, is a current or a voltage which looks like this. So it's always in the same direction. It is not changing direction. Now additionally, we can also see here that this magnitude is also fixed. But remember that that is not a requirement for a current to be called direct. The only requirement is that the direction should be the same. So strictly speaking, if instead of what I had here, if I have something like this, if we have something like this is also direct current, right? Both of these are going to be called DC because fixed magnitude is not a requirement. It could be, and that's good, but it's not really a requirement. What we have above, where the current or the voltage is always positive, it's always in the same direction, this suffices for it to be qualified as a direct current. Now, on the other hand, if we talk about alternating current, so alternating current is bidirectional. Obviously, with currents and voltages, you can either have one direction or you can have two directions. You can't have more than that. So in this case, the current flows, or rather we should say the current, since this is alternating, it alternates between its directions, right? So whatever the two directions has, the two directions which are there for the current or the voltage, so the current keeps alternating between them, so its direction keeps reversing. So usually, and this is also what we get in our homes and our electric supplies, is a sinusoidal voltage. And if you remember that shape, so this is how it looks like. This one is called a sinusoidal, so a sine shape. And I hope you guys remember your trigonometry, graphs and equations, all that stuff that we studied in simple harmonic motion, because we are going to be needing it here. But this is not the only type of shape we have, although this is the most common one. There are other shapes as well. There's also a shape like this. This is called a square wave. Again, as you can see, this one is also reversing in direction, and additionally it's also reversing in the magnitude in a way. Strictly speaking, in this case, maybe the magnitude is not changing, because whatever this value is in a square wave is also equal to this value. So if this is some V naught, so this is also V naught, but just with a negative sign here. This is also the same thing which happens here. So if this is V naught, then the negative, the minimum basically is negative V naught. So that's how this is. And another shape that we also encounter in real life is something that looks like this. And this is called a sawtooth wave, because of how this looks. So these are some different types of alternating currents. In our syllabus, our focus will be almost exclusively on the sinusoidal alternating currents. And just like how we talked about this in the case of simple harmonic motion, the current can be written in this way: I naught sine omega t. If you remember, omega is the angular frequency here. And similarly, the voltage can also be written as V equals V naught sine omega t. So since the current is frequently changing its direction, what we say is that these electrons in the wire, in this conductor, are also moving with simple harmonic motion. So it goes like this one way, and then it frequently goes like this. So that back and forth movement is why we are having simple harmonic motion back into our conversation again. So omega is still defined exactly as how it was previously. You can write it as 2 pi over the time period, and you can also write it as 2 pi f. So the angular frequency is 2 pi times the linear frequency. And this I naught and the V naught are the peak values of the current. Let's have a look at this equation through a graph. So we have V or I. Again, it doesn't make much of a difference exactly what we're talking about. The same ideas apply both ways. Let's just make this a bit easier to work with. So the sine graph you're already familiar with. So this is basically the amplitude is the peak voltage, and because of how a sine graph works, because of the vertical symmetry, this is negative V naught. So the same magnitude but opposite in polarity. And this distance, as we've talked about previously as well, so the horizontal distance here, either between the peaks or the crests or the start of one wave and the start of another wave, that's the time period, capital T. And from that you can get omega for use in this equation, which is shown here. Let's have a look at an example question for this. So this question says the variation with time t in seconds of the potential difference in volts of an alternating supply is given by this equation, 24 sine 380 t. So if you just compare this with what we just talked about, 24 sine 380 t. So basically the amplitude of the wave is the number in front of the sine or the cos function, that's the amplitude, and that is the peak voltage. So I can immediately identify here that V naught is 24 volts. So this is the maximum voltage. In the positive direction it would be plus 24, and then in the negative direction it would be negative 24. And here we have omega, which is 380, right? And if you remember the units for omega, so it's radians per second, because omega is what? The angle swept out per unit time. So radians, the angle in radians divided by the time. So part A, the peak potential difference, it's very easy to see. This is 24 volts. This is usually called V naught. Part B, the frequency. So we have omega is 380, and we know that omega can be expressed in terms of the frequency as 2 pi f. So 2 pi f equals 380. So then for f, we just need to have 380 over 2 pi, and that's going to be the frequency in hertz. To 2SF, this turns out to be 60 hertz. And let's say, even though the question is not asking for this here, let's say that if we also want the time period, so that would be 1 over f. So 1 over whatever this was, you can also probably see this is 2 pi upon 380 basically. That would be the time period. So 60 point whatever this was. This turns out to be 0.0165, so 0.017 seconds, correct, to 2SF. Now let's say that if you had to make a graph for this voltage function, then it's going to be exactly the shape that we just looked at. So it's the exact same graph, only now this is just a V graph, and this V naught and minus V naught, you know, are the peak potential difference values, the peak voltage values. That was 24 in the positive direction, and then in the negative region it would go as low as negative 24. And also, if this is a time axis that we have here, so if this is the time axis, then we can only have the time period here. So one full wave is formed in 0.0017 seconds. Then another one would take another 0.017, so 0.034. And this is another half wave. So just increment this by half of this. Whatever this turns out to be would be this time value. And then obviously this time period, this gap would also be 0.01 seconds, as we've discussed before.